Okay, so good morning, everyone. I'll start with a brief reminder of where we were last time. So we were discussing the generalized log-level trial model with random parameters, and essentially we saw that there were two control parameters that were dictating the phase diagram. So we had mu, which was the mean of the interaction coefficients, then sigma, which was square root s times the standard deviation of the interaction coefficients. There was some value sigma c that we, in some cases, simple cases, we determined. Here is the value 1. Essentially, this was the phase diagram. So here we have a fixed point. And here we have fluctuations. What I was showing you is that in that region of the phase diagram, when there is no migration, so that was the original system that we looked at. So the dynamic was aging. And we could describe it in terms of a limiting process for in log time for variable that I call z, which was the log of mu divided by t. And it's a non-Markovian random walk confined to the negative region by Arnoulx. Here we have a Arnoulx. And that's provided that there is no mechanism for extinction. Otherwise, these large fluctuations that effectively at large time are exponential in time towards small numbers would lead to extinctions and to the suppression of fluctuations. And then what we discuss at the very, very end is that if you have migration, so migration would be in the form, let me remind you, of d nu I d tau is equal to nu I. So that was the system that we looked at. Minus sigma square root s sum over j, different from I. Z ij nu j plus lambda. So that's what I was calling the migration rate. So if lambda is strictly positive, then we have chaotic dynamics. And numerically, it was shown that the maximal Lyapunov exponent in that region of the phase diagram is strictly positive. So that's really chaos in that sense. And when lambda goes to 0 plus, similar reasoning to the one here shows that there is a limiting process in terms of the variable t, which is log mu divided by log lambda, and time divided by log lambda, which is similar to this one, except that now it's described in terms of a random walk with two hard walls, one at -1, representing that the fact that population sizes cannot go below lambda, and one at 0, which is due to the self-confinement.
So the computation of the Lyapunov exponent.
So computation, numerical estimation. Okay. There's no analytical results.
Even, for example, the looking at the Lyapunov exponent, nobody wrote, or it's written somehow. I mean, if you
I mean, I don't think, the thing is that I don't think you can write a Schrodinger problem in that case. For the same reason that you cannot write a classical mechanics problem for the correlation function.
Okay. But I mean, it's still a 4-point function, so there should be some kind of like better equation or something like that.
Yeah, I mean, I don't think anyone wrote it. Okay, so this is where we were. And that I was telling you because this is a very crude way to implement space, saying that you have individuals coming from the inside, from the outside into the system. So this sort of points toward the way that spatial extension is crucial to understand the existence of many species coexistence and fluctuations. But obviously here, nothing tells you why diversity is maintained on these larger scales so that you have a constant migration rate here. So this is something that we need to investigate. But before that, I wanted to go back for some time in the fixed point phase and discuss something a bit different, but which is a very nice line of work, I think, which is about the statistics of the interaction matrix in the fixed point phase. So what do I mean by that? If you look at the full species pool, so the S species with which you have initialized these dynamics, lambda equals 0. So the interaction matrix is random. And specifically, we took it Gaussian. 0 mean with Zij, Zkl is equal to, I think I was using averages like this, is equal to delta Ik delta Jl plus gamma delta Il delta Jk. That was the original ensemble of the interaction matrix. Now, the realized interaction matrix, and by realized, I mean the one that you can actually hope to measure, which is the one between the species that have survived the selection process and the convergence to the fixed points. So this is restrictive to surviving species. Is also random, obviously, still a random object, but with different statistics. And so its structure is affected by the dynamics. And so the question is, what is the signature on the interaction matrix of this selection process? So more specifically, what I want to look at is the following. So one is, but that's just an example, the expectation of Z01, so the effect of 1 on 0, conditioned on the fact that we've observed nu 1, nu 0. So that's the fraction of 1, that's the fraction of 0, which are both positive, and some at some value. So this is conditional average.
Equal time.
So this is in the steady state.
Ah.
This is in the fixed point phase, and this is in the steady state. You're right. That's in the steady state at the fixed points. And so this, if you just use base formula, it's D01 times Z01 of so the probability in the original ensemble of Z01, that's probability in the original ensemble times the probability to get nu 1, to observe nu 1, nu 0 condition on the value of Z01 divided by the probability to observe nu 1 and nu 0. So this is the object now that we have to compute. So what we want to get is this conditional probability. And so more generally, for the kind of object that we can compute, or that we would be interested in computing, given the finite set of species, I, so the set, I'll put it capital I, we are interested in computing the expectation of, if I look now at this object, this is the expectation of, so I can take a generated function, sum over I in I, sum over j, different from I, belonging to I, the ij, lambda ij, times the conditional probability to get nu I, given the value of the interaction coefficient. This is the kind of object that we would be interested in. And then taking derivative with respect to lambda ij allows us to get the moments that we would like to evaluate.
But sorry, this is directly large deviation on the data.
So it's not large deviation.
But
There's no large deviation factor here, so we're probing typical.
lambdas.
Yes, it's a characteristic function, but I'm saying that lambdas, I want to take them as being order 1. So there's not a large deviation regime that I'm interested in.
Okay. But so if I
Just
take,
moments like this.
yeah, but if I take the original model, what I'm asking is, I take the dynamical equations,
Yep.
and then I just look for positive solutions of the fixed points.
Yep.
So I just need to erase columns and rows of the matrix. And the thing, I guess that there will be many solutions of that, so that I can eliminate many rows and columns, but most of the things are.
No, because in the fixed point phase you converge to a unique fixed point. So that's
No,
the
but
that's the one reached by the dynamics.
which is the one that is attractive, where I could have like solutions that that are all positive and zeros for the nus, but that the dynamics doesn't select
Yeah.
because they
And that's not what I'm interested in here. It's not the solutions that I'm looking at. Here I'm looking at the dynamics, assuming that you converge to a fixed point, you're in the fixed point state, so this fixed point. And then I want to know the statistics of the z's given the realized values of the news at that fixed point. And so, I was showing you, I think 2 lectures ago, how one can derive the dynamical mean field theory equation with the path integral formalism. So you can basically use the same formalism to compute objects like this. I'm not going to redo the whole thing, but a direct extension of the generating functional approach used to construct dynamical mean field theory. And here, for instance, that could be a good reference for that extension. So Baron, Jewell, Ryder, Gala, 23. Shows that conditional moments of the Zij, given the value of the new i's, can be computed that to leading order in S by considering the end result is fairly simple. The joint equation mu I dot is equal to mu I gamma plus delta Ri minus mu I plus sigma psi I gamma square R tau prime mu I prime minus sigma divided by square root S sum over J Zij mu J. Where, and I'll comment on this, where I tau are IID Gaussian processes with, so I tau, I two prime, I'm going to call it C tau two prime. And where the kernels C R and gamma, which is here, are solutions of the original DMFT. So in other words, what I'm telling you is that if you look at the dynamics of a single species, the single process, this is what we wrote. This is the equation that we wrote with psi Gaussian process correlation function C, R kernel, and we had a set of equations that are specifying C and R. What I'm telling you is that if you want to compute the conditional moments of the Zij knowing the news for a group of now, let's say you have 3 species, the only thing that you need to do is to look at couplings of these different processes that are coupled by the coefficient Zij, but still the rest is the same as given by DMFT. And that's enough to the leading order.
Also, if I indicates with S, they said.
No.
So what I mean, this is like for I don't know a finite number of
Yeah, a finite set of species.
Okay.
Yeah. Otherwise, you run into the same problem as the. I mean, DMFT doesn't work if you want to compute.
But in principle, why should you go to the dynamics? Or can't you directly do the computation from the fixed point equation?
No, you can. I would say that's the general thing, because from there you can directly go to the fixed point. Just that the fixed point equation, you have to deal with the conditioning, right? That some species are going extinct, some are not. So it's a bit more tricky than following the dynamics in that sense. But that's a personal taste, I would say. Both are possible. Okay. So now, for simplicity, let me focus on the case gamma is equal to 0. And so remind, the first observable that I wrote, that's the one that I'm going to be interested in, is the average of Z01 knowing nu1 and nu0. So it's just a two body problem. So in the fixed point phase, what we get that when given that nu1, nu0 are larger than 0. So this is 0, this is not 0, so we need to cancel this. This is equal to 0. So what we get is nu0 is equal to gamma plus delta R0 minus sigma Q eta 0. And I'll write minus sigma square root S Z01 nu1 with eta 0 Gaussian variable with mean 0 and variance 1. So it's here, and where Q squared is equal to the average, to the variance of psi. So I'm just pulling out the Q and writing it in terms of the normalized Gaussian variance. And that's a number that we know that's given by DMFT. That's something that we computed 2 lectures ago. And now you have the same equation for nu1, gamma plus delta R1 minus sigma Q eta 1 minus sigma square root of S Z01 nu0, and where eta 1 is an independent process. Independent variable, also mean 0 variance 1. So now, if I call this the unperturbed value nu1 0, and this nu0 0, to the leading order, you get that the conditional distribution nu0 nu1 given z01 and z10. Sorry, so here it's z 1, 0, the action of 0 on 1. That's equal to beta 1, beta 2 to the leading order, delta mu 0 minus mu 0, 0 minus sigma square root s 0, 1, and mu 1, I can replace it by its leading order value. And then the same thing here, mu 1, 0 minus sigma divided by square root s z 1, 0, mu 0, 0. With the condition that these two things are positive. One, this is 1, 0, 0. So this is just a normalized Gaussian. And from there to the leading order, you can compute the expectation of z1, 0, or rather, let me do it directly. But you can compute from there, just a matter of expanding this delta function, the expectation of z1, 0, condition on mu1, mu0, and you will find that it's sigma divided by square root s mu 0 p prime mu 1 p mu 1.
Sorry.
Yeah.
What is that? Eta 2? I don't understand. Is the problem an index?
Ah, maybe. If you say eta 2, there is probably a product index. Yes, sorry. Here?
Yeah.
My bad. Thanks. It's 0, which is in this one.
Okay.
The problem is very non-symmetrical.
Yeah, exactly. So I'm gonna comment on that. So in order to see a bit more what's happening, let's assume
So Z10 and Z01 are completely uncorrelated in the original.
This
So
gamma,
in the original ensemble, yes.
this is gamma. If gamma equal to 0,
Yes, gamma is
Ah.
0.
that's,
okay, so gamma equal to 1 would be the same. No?
Between mu 0 and mu 1?
Yeah.
Yes.
No, okay, so it's symmetric.
It's asymmetric.
It's asymmetric, not antisymmetric.
So let's assume that delta r is equal to 0. Okay, so maybe something that's first. So let's do remarks. One, let's imagine that I want to now constraints. Now I'm just interested in constraint in the survival of 1, 0. What is the expectation of z01? So I'm just saying now that both species survive. I have this table of interaction coefficients. I want to know the average of Z1, 0. So you can average over this, and what you will get. So now I need to average over the probability to get nu1 and nu0. So this one will give the average value of nu0. And this one, when I average over nu1, so I multiply by p nu1, that goes away. I just have the integral of p prime. So that's minus p of nu is equal to 0. And because I'm constraining on the fact that these guys are surviving, I need to divide by the fraction of surviving species at some point. What I want to insist on is that this is negative. And so the conclusion is that the surviving community is on average less competitive than the original pool. So the selection, the species that you select has a bias towards things that are less competitive against each other compared to the original ensemble. And this is what allows for survival of species. Now coming back to the asymmetry that you were mentioning. Let's assume that delta R, because it's slightly more clear, but you can make the same argument already at this level. Delta R equals 0 for all species. I'm saying that because in that case, we have an explicit formula for the P of nu, which is this truncated Gaussian distribution. And so I'm just reusing results that we saw before. Minus 1 divided by square root s, nu 0, sigma hat nu square times nu1 minus k. So using the truncated Gaussian distribution. The exact form is not so important. But what I want to comment on using this formula is the following fact that, so this measures the interaction of, the effect of 0 and 1, right? So the conclusion is that competition or interaction with unsuccessful species, so if I'm saying unsuccessful, it's low nu 0. Is weakly biased. In the sense that if nu 0 is small, then the bias observing nu 0 and nu 1, or the bias observing nu 1 on Z1 0 is small. However, if you take two successful species, so large nu 0 and large nu 1, two successful species are less likely to compete against each other. So that's large mu0, mu1. Or complete less on average than the other. That's the first thing.
Before you have reached the kind of facts, ecological facts, is this checked in nature or in fact?
There is one check I know of this. I'll tell you more at the end of this. So now we can apply the same technique, I mean the same thing with a two species problem. The same reasoning to show that to the leading order, the expectation of z01 square given u1, u0 is equal to 1. And the expectation of z01, z10 given u0, u1 is equal to 0. The variance, or variance, or let's say second order moments are not modified compared to the original ensemble. And if I had kept gamma non-zero, I would have found gamma here as expected. So the variants are not modified, and that somehow explains why something that we used before to explain this stability condition, why the bulk explains the big word, but why the bulk of the eigenvalue spectrum of the realized or restricted interaction matrix is the same as that of a random subsampling of the original one. You still get the elliptic ensemble or the Guillermo circle if gamma is equal to 0 with the extent of the circle is exactly the one that would predict just from a random sampling. Yes?
Moments or cumulants? Moments?
Moments. I mean, if you want to compute cumulants, then you have to take into account this.
Yeah, exactly.
So, but you see that the cumulants will have deviation with respect of order 1 over s. So this is really moments that I'm saying to the leading order.
Okay.
Cumulants to the leading order would have the same value. I mean, not for this one, because for this one you would have a small correction.
Okay, yes.
But that's why it doesn't change the bulk. Yes. But we're going to see it's a bit more complex than that. So that when I say explains, here I want to put, because, I mean, it's more refined.
So you mentioned that I do the other thing. So you mentioned that I start from the original problem. So in this case, I start from S species, and then I get pi times S species at the end, and then
yes.
One thing that I can do is that I say I start with S species, and I look for the large deviation of the Z, such that the surviving species are exactly S.
Yep.
Would I get the same statistics?
As s goes to infinity, yes. Yeah, this is something I'm planning to comment on.
Okay.
Or I think it's the same as what I'm planning to say. So let's see when I'm there. But I think it should be the same.
Which is, I mean, the result is kind of reasonable in the sense that if you want to make S the surviving species larger, you need to plant a little bit
Exactly.
of ferromagnet
Exactly.
in the needle, right?
Exactly.
So that should be a little bit of ferromagnet, which is exactly.
Yes. But we're going to see that it's a bit more complex than a ferromagnet. And now I want to speak about patterns of correlation. So now I want to look at higher order variables, and or not really higher order, but we can look at the emergence of correlations between elements bearing only one index. And this is, I mean, those correlations are zero in the original ensemble. So what I want to compute is the covariance of Z01, Z02, given mu0, mu1, mu2, and the covariance of Z01, Z20, so here I'm inverting Z2, given mu0, mu1, mu2. So to proceed, so we just need to introduce now the free species system. And I'm assuming that at a fixed point, with survival. And so the system that you have to solve is this one, minus sigma square root of s Z01 minus sigma square root of s Z02 Z1, 2 Z2, 0 minus sigma square root of s Z1, 1. This is mu0, mu1, mu2 is equal to mu0, 0, mu1, 0, and mu2, 0. With, so as before, mu I, 0 is gamma plus delta I minus sigma q eta I, where eta i's are this. So this is the system that we have solved. And okay, I'm sparing you a few computations that really don't have anything fancy once we're there. Just gonna state the results on the covariance. So if you look at this, you will find that it's -1/s to the leading order. So these are still small numbers when s is large. μ1, μ2 divided by mu square. But that if the indices are reversed, the covariance is equal to 0. Independent. So what does that say? Let's imagine that I have two successful species, which are μ1 and μ2, and I'm looking at how they compete on 0. So if one competes more on average, then the other compete less on average, because this is negative. So two successful species are less likely to compete against the same target. Or rather, formulated in a way that's probably more intuitive, that tells you that the species that is strongly competing with two successful species has actually a high chance to be extinct. And so given that you observe it and that it's not extinct, you deduce that, okay, it's not competing, I mean, on average, it's not competing strongly with different successful species. And so now I come back to your question, Ivan. I wanted to discuss the results of the paper. I mean, this is already in this paper, but the experimental results of the paper. So it's called fingerprints of high dimensional coexistence. And it's direct 2021. So in that paper, what they did is that they analyzed, so it's analysis of the results of a grassland experiment. So it's on grass. The system is on grass. The experiment was not designed for this analysis, but it ended up being quite appropriate. So in the experiment, and these are quite small numbers, there is a pool of 8 native species. The experiment is in some region in the Netherlands. And essentially what it is, it's a large number of plots. So you're in a field. I think the plots are 1 meter by 1 meter. So it's in a natural open environment in which plant species are assembled. In varying number and combinations. So essentially, what you have is you have a plot where you know that you have species A and species B, and every once in a while, people would come and take out all the roots of species C that they see because the thing is open. So you need to preserve the fact that it's just a two-species system. And so you do that for single species culture, you do that for two species culture, you do that for a bunch of 3 and 4 species, and you do that for the 8th species culture with several replicates. So what you can do in this experiment is to use two species plots to estimate the interaction coefficients. So you estimate them from two species combinations. You have also one species plot where you know the total biomass, so the carrying capacity reached by individual species. So you need also that information, and you can extract the interaction coefficient. The first thing that they checked is that the alpha ij estimated correctly predict abundances in the S equal to 8 plots. And all those things I forgot to say, small number of species, they are all at an equilibrium. The population sizes of the different species don't vary over time. So that's a good indication that at least in this system, higher order effects are negligible. That you estimate your coefficient from a two-body problem, and then you can generalize to assemblies of more than 2 species.
Sorry, so what they do is that they put just 2 species, they look at the
Exactly.
they compute alpha.
Exactly.
And take the 8,
and then they use this. I mean, so you have the abundances of the 8 species empirically, and then you have the prediction given the alpha ij that you estimated from the 2 species, and that tells you what is the abundance of the different species that you should see, and it matches. And now coming back to what I was discussing, now that they have an empirical matrix, they can essentially successfully compare mean correlations of alpha ij to theoretically predictive patterns, which are the ones that I was describing before. So if you have 2 strong species, I mean the correlation Z01, Z02, the covariance is negative correlation between the 2, assuming that the species are surviving, and also I mean this thing with the mean that you're not biased if you're in your competition with unsuccessful species, but the more successful the species is, the more biased tends to be your interaction coefficient.
What is the number of species that survive for S equal 8?
They all survive.
Okay.
Because it's, I mean, the rationale is that it's a natural environment, so somehow the selection process has already taken place. And so what you see and what you grow in those plots are things that can coexist together, so they are already the outcome of this effective dynamical thing that you don't see. But the way they formulate it is a bit different, and that's where I was coming, because all of this is for infinite S. I mean, that's the largest regime. Here we have S equal to 8. Okay. So the way they actually did it, to be more precise, and it captures some finite size effects, even though in the S to infinity limit, the results are the same. I mean, I'm just going to state it. So what they actually did is saying that, okay, imagine that you have a prior distribution on the alpha ij, which is this uncorrelated Gaussian that I had at in my initial ensemble. Then I'm saying that essentially what I have is this, right? I have 1 minus nu I minus sum over j alpha ij nu j equal to 0, and I'm seeing nu I nu j. This is what I'm measuring, right? And so what you're saying is that the distribution that you're actually seeing is using Bayesian inference, the original ensemble condition on observing these values of abundance. It's sort of a maximal entropy principle given the values of the abundance that you've seen. And that's what they actually compare with the data. It turns out that when the number of species become large, the predictions for the patterns of mean and correlations are exactly the same as in the random GLD and the community that survived at long times. So that's going to close this discussion on the fixed point phase and a bit more certain things that can be done in order to study this fixed point phase beyond the species abundance distribution and the boundary of the phase. So I'll stop here before the break because then we're going to move to something quite different. So I don't know if you have questions, please ask them, and otherwise we can go for coffee or a glass of water.
That's super naive question. So there are only plants. They are absolutely sure that there are no bugs, no insects, no
No, that they don't control. That would be part of the environment.
Okay.
So I guess that yeah.
They integrate out.
Exactly. Yeah, the environment is integrated out, effectively summarized into this coefficient. Indeed, you can imagine that, I don't know, some plants attract some bugs that are going to eat another plant. And so effectively, this plant has a negative bias,
The other one. Yeah.
but it's still in this one. Effectively.
Okay, so very remote question. So somehow in physics we always consider binary interactions, essentially always. But for instance, biologists would tell us that it's not the ecology, cells, whichever. So almost all reactions are like thermal or more because we catalyst, whichever. And for instance, at least some your techniques are somewhat more or less resembling walk on glasses, for look at this. And over there, they actually came to this non-spin interaction. It's important that the analyzing inside. Then one, but okay, can through box whichever effectively three body interaction, whichever high body interaction.
So
Do people look at think study?
yeah, definitely. I mean, in the empirical literature, it's well known that these higher body interactions exist in ecology. There is a bunch of results on that. If you think about, I don't know, behavioral interactions, that the presence of one species scares one species from going there, which is where it would be eaten. I mean, this kind of thing is very present. So effectively, you do see them. So far, in the setting of multi-species models, I mean, some people have tried to implement that. Maybe I missed some things, but I don't think I've seen anything that would radically challenge the qualitative conclusions that you get from the two-body picture. Obviously, there are some quantitative differences. There are some subtleties. The nature of the, I mean, we know that if you're with perfectly symmetric interactions, the kind of landscape that you would describe would not be the same with p-body interactions than with two. But I don't think we have an evidence yet that this is that this could really change the whole picture at the theoretical level. Maybe, but it's not clear to me.
My main concern is that this so the things that are by J stuff, which okay, so for I don't know, maybe for a small system like this that is already selected by nature, and then you have like then you
So
have
in stationary over time.
stationary over time and independent of the other species abundance.
Yes, that's the nature of the pairwise.
But I mean, one could think, I mean, so this
If you
is
start saying that alpha ij depends on the abundance of the other species, it's like higher body interactions, right?
but then I mean, so I mean, if you think about a model where you have also resources, then it's more clear that I mean, if you have some I don't know metabolism to live, then you need a set of resources to live, and so there the interactions with resources is kind of constant. Or I mean, it's like some game strategy that you fix it. Maybe you have a pool of strategies to survive, but they are fixed. And so in that case, I tend to agree more with the modeling. But here, I mean, it's kind of surprising that that I mean, I guess that go to bigger system size and so on. I mean, and spatial effect stuff can start to play an effect and so on. Maybe this alpha j constant.
Yeah, I mean, okay, so there I would say that there are really two ways to approach the problem. The thing is that, I mean, the way I tend to see things with all these ecological problems is that if you start to look at the microscopics, you can only be dazzled by the intrinsic complexity of the thing, and you can imagine pretty much everything. Every refinement is possible. You will find a system where every kind of refinement would actually be at play. So the question, I think, is rather, if you think about this high dimensional stuff where you expect to see some features of universality emerging, what can really change? What can you really challenge by doing that?
But I mean, even here, what's the thing that you really touch on this? I mean, it's not high dimensional. It's
I mean, here?
yeah. I mean,
Yeah, okay. So
what's the question you're answering?
I mean, here it's interesting, I think, to see that the kind of thing that you see in this natural community is actually pretty compatible with somehow the least ordered model that predicts the right abundances. That's essentially what it's saying. So there is no strong, like it's an instance in which here interactions are diffuse, everyone competes with everyone. There's no strong low-dimensional structure. I mean, you can't say that there is one nutrient, everyone is competing with this nutrient, and that's the only thing that matters. I find it interesting in that way. And you do see, I mean, in the paper is quite complete. They do the whole finite size analysis, and they see that, I mean, the variance of the coefficient that you find is, the amplitude of this variance is compatible with, I mean, the deviation with respect to the mean is compatible with what you would expect from a random interval of this size, how it deviates from the mean. Like, quantitatively, actually seems to work.
So S equal 8 is close to S equal
So it doesn't work. It doesn't work with the S infinity predictions. It works with the. It works for the finite S random ensemble, maximally disorder. But it's still finite S in that way.
but the finite S random ensemble is not what. So you have
No. So that I was saying, you had finite S corrections. They take that into account.
Okay.
What I'm saying is that, I mean, the behavior is the same. Like qualitatively, the direction of these biases is the same. And quantitatively, when you set S to infinity, you find what you predict in the random local trap. But they do take into account the.
With S equal to 8, you can just solve the numerically the problem. You don't need.
Yeah, you need an ensemble.
Yeah.
You need an ensemble, and this is the ensemble
solve
of the numbers.
numerically.
I think you can solve it. I mean, you can, yeah. Right.
Online.
Cool. Okay, so now I want to go to something different than I was telling you just before, and to discuss, at least in one framework, because this is, I mean, this starts to go towards places where things are less established, but to discuss about the role of spatial extension in those models. So now relaxing the assumption that things are well mixed. And for reasons that will become clear later, I've called this the stabilizing role of space. So what we've seen before, coming back to this little summary that I was making at the beginning of the first hour, is that non-equilibrium coexistence. So non-equilibrium coexistence is very atypical in well-mixed closed ecosystem models. So here I'm speaking about high dimension random interaction. So because either you have a fixed point, you're in the fixed point phase, or you have this very large aging fluctuations where and species get killed off. Eventually you converge to a fixed point again once you have extinctions. And so concomitantly, the number of surviving species is bounded by the stability boundary of the fixed point phase. And so that's like a form that is S star, so that's the number of surviving species, times the variance of the interaction coefficients is less or equal to some order one number. And I'm being very sloppy here. To be more precise, for instance, with asymmetric interactions, you get that the number of surviving species times the variance is less than 1 minus the mean. If the mean is smaller than 1. If you have some degree of symmetry or anti-symmetry in your interactions, there would be some coefficients here, depending on gamma, but that's still what I'm calling an order one number. So in principle, I mean, if you have a mechanism that makes that the variance scales as 1 over s, that's the scaling that we took before to really see the fixed point phase, you can sustain a large number of species because then you have a finite fraction of surviving species. If you start saying that, okay, the variance is actually some number, and you want to start packing species, then you will hit this bound, and that will set a limit on the number of species that can exist. So that's the first thing. So what we have also seen, we have also seen that with external migration, so constant, it is possible to stabilize the chaotic phase where everyone survives. But as I was saying, there's no mechanism in this to explain why things would survive outside. So the first thing that I need to stress is that the complete theory for spatially extended models of that form, high dimension, random interaction, is largely missing. And in this chapter, I want to discuss a simpler setting in which things are quite under control. In this chapter, we discuss a setting, and this setting, I'll explain why afterwards. It's denoted as time average neutrality. Where things are under control. And we can start to approach what's the effect of the spatial structure underlying the model. Even though it's R under control, it's like R under control in some simple setting. But okay, let's see. So I'll start by the Latka-Volterra dynamics. So very simple, 1 minus sum over j, alpha ij and j. Okay. With the simple structure, alpha ij is equal to mu if I different from j, and alpha I is equal to mu plus epsilon. So no disorder in the interaction. The case epsilon equals 0 is called neutral. And what does it mean? It means that essentially because this now does not depend on I, it's mu, it just depends on the total sum over n. Okay. So it's saying that the birth rate, the combination of the birth rate and death rate of any species, of any individual belonging to any species, is actually the same. So this is saying that it's a very special point where individuals are equivalent. There's no difference there's no difference between individual of species A and species B. It's just that A and B are labels that each of them is passing by to their offsprings. But the labels have no actual meaning. So in this system, there is a coexistence fixed point. Its value is 1 divided by mu s plus epsilon. and it's stable for epsilon larger than 0. So it's that intra-specific competition is larger than interspecific one. And in fact, the Jacobian has two eigenvalues. One which is lambda 1 minus epsilon r divided by mu s plus epsilon, and lambda 2 which is minus 1. And this one, it corresponds to modes that preserve the total biomass.
What's the area?
Sorry, it's not here. In my notes, they had kept an R here, but it's really just a factor of time. So it corresponds to modes that preserve the total biomass. So as R, as S becomes large, or epsilon becomes small, the total biomass is very constrained, but the system starts to become a bit soft in the ways you spread the different species to keep this sum at a given value. And so when epsilon is equal to 0, the fixed point is marginal. Okay. Here, nothing really happens.
For epsilon 0, you want to claim just one fixed point.
Sorry?
For epsilon 0, you claim just one fixed point, not a manifold of fixed point.
So when epsilon is equal to 0, there is a manifold of fixed points. It's just that the total biomass converges to 1, but then the fraction is the same as in the initial condition. The fraction of each species doesn't change.
Sorry, and where is space?
It's coming. It will take some time to appear. Yes, because I need to introduce them all without space first. Okay. And so, still no space, but we now seek to analyze the dynamic, because here nothing is happening, it's quite boring, in the presence of noise.
Sorry. What's the degeneracy of the two eigenvalues? I don't
Yes,
see.
this one is 1, this one is s minus 1. And so what I want to look at is dynamics driven by environmental noise. And the relevant reference for this part are the following: Malmin, Aldi, De Monte, Ecology Letters, 2026, and Bernard Bouchot, Le Doussal, ERP, 2026, and this one is for a related model of, I think, city growth. So it's not in the ecological context, but the framework is very similar. And so what I want to look at is the following. So I want to look at ni dot is equal to ni r. So if you don't mind, let me reinsert r here. So we have an r everywhere. R plus sigma phi of t minus epsilon ni minus sum over j mu and okay. So this is the environmental noise that we saw at the beginning of the lectures, and I'll assume that I have psi I t psi j t prime is equal to delta ij delta t minus t prime. So I'll take it as being Gaussian white noise. So here, it's quite in its form, it's quite reminiscent, at least written this way, of the dynamics that I was discussing with random interactions. Because effectively, with random interactions, that would behave like the mean, so that would be something that self-averages, and you would have a Gaussian noise, an environmental noise. So it's similar to the dynamics with random interactions. But, and that's a big difference, without the self-consistency condition. Because like with random interactions, you say that the correlation function of the noise is equal to the correlation function of the variables that is being driven by the noise. Here I don't say that. And one way to think, sort of rationalize this model, would be to say that so the underlying rational that there is a large number Q of fluctuating environmental factors. I don't know, temperature, pH, think about several of these. And the growth rate of the different species respond to fluctuations of these factors in ways that are not correlated. What I want to say here is that imagine that you have just one thing that is fluctuating, the temperature, and that the growth rate of the different species is temperature dependent. Here you would say, okay, so here there would be a coefficient, I don't know, Qi times the fluctuations of the temperature, but then the effect, I mean, the noise acting on the different species would be correlated. So in order to get something where you don't have correlations, you need to start saying that, okay, you have many things that are fluctuating, and they add up in ways that are incoherent between the different species, so that when you look at the net effect, they are not correlated. That's the sort of idea behind this delta ij. And now I want to, so that's the model I want to analyze, still no space. And the right way to look at it is as for a Latker-Boltzmann model. So we introduce the scaled relative abundances. So it's mu I is equal to S Ni Nj. So that 1 over S sum over J mu J is equal to 1. And I'll write M, the total biomass, is equal to sum over J Mj. If you rescale time, you get the following set of equations. d mu I d tau is equal to mu I. Gamma, so it's very similar to the ones we had before, except that this is a unit variance quotient white noise. Epsilon divided by sigma 2s times m mu I. Gamma is epsilon sigma 2s m 1 over s sum over j mu j square minus 1 over n sum over j mu j j, and dm d tau is equal to 1 over sigma square m 1 minus mu m minus gamma n. Okay. In these variables, this is the set of equations that you have. What emerged from this? Is that if you want to get the fluid generic, and it joins what we were saying on the Lotka-Voltra model, in order to get the state of full coexistence, and by that I mean the state where P nu is equal to 1 over S delta, so the empirical distribution has a well-defined limit as S to infinity. This is what I'm interested in. You can start taking species, okay? What you need is it is necessary to work at fixed epsilon hat is equal to epsilon divided by square root sigma square.
And this definition of capital gamma separate
Thanks. Sorry, it's I think it's 1 over S. Yeah. Thank you. Okay, so you need epsilon hat to be constant. So either a mechanism that increases with S the amplitude of self interactions, or a mechanism, so the amplitude of self interaction is epsilon, or a mechanism that reduces fluctuations and that's sigma. If epsilon is fixed, then as S goes to infinity, I mean, you have convergence in law of this, and the different, the dynamics of the different species decouple. And so you can obtain P of nu as the steady state of d nu d tau equal to nu gamma plus psi minus epsilon hat m nu, and m has to satisfy this condition. Minus gamma m equal to 0 with, and now you have to solve for gamma, and with gamma is equal to epsilon m, ensuring that the average of nu is equal to 1. So from there, as in the first lecture, we can find the P of nu. So we have P of nu up to a normalization constant, which is E minus 2 nu epsilon m times nu minus 1 plus 2 epsilon m. And so what happens when m goes to, obviously this distribution has no limit in terms of a distribution, of a top probability distribution when epsilon goes to 0, because it's not integrable both at 0 and at large population sizes. So no limiting probability distribution when epsilon goes to 0.
And when you raise proportional, you mean equal up to the amplitude? Yeah.
It's normalization constant. Yeah.
Because, yeah, so maybe it's very large, no, very initial.
And in fact, so it's easy to show that for epsilon very small, the probability to get nu larger than some value gamma divided by 2 epsilon m, that's roughly 2, so it's a small number of order epsilon times something that is finite. And now in the original model, where I have no reason a priori to assume that epsilon is going to grow with s, like this, the bare epsilon, so it's epsilon of the order of 1 over s, taking epsilon of the order of 1 over s corresponds to a state where the mass condensates on a finite number of degrees of freedom. Because the probability to be of order s, meaning that n, because n is nu divided by nu is n divided by s, the probability to be of order s is of order 1 over s. So eventually you have condensation of a few finite degrees of freedom with this scaling, and accordingly, if you compute the mean of the log, you get something which is order of 2 epsilon hat. So that corresponds to exponentially small values of typical population sizes. So in fact, at finite epsilon sigma, the system in the large S behaves as its epsilon equals 0 counterpart. Because eventually here, this is epsilon divided by S already. So when S is large and epsilon finite, this goes away, like in epsilon equal to 0. And when epsilon is equal to 0, the dynamics is going time average neutral. The neutral system on which you have added invariant fluctuations that whose average is 0 over time. So it's time average neutral. And for epsilon is equal to 0, it's interesting because the dynamics can be solved exactly. And it sort of helps understanding this other limit of condensation. Because when epsilon is equal to 0, what you get is the following: mu I gamma plus psi I of 2. And so as before, where gamma imposes that 1 over S sum over J mu J is equal to 1. And that I can integrate it, it's linear. And so what you get is that mu I of tau is equal to, okay, assume that mu 0 is equal to 1 for all species. If you have a distribution of, mu I 0 is equal to 1 for all species. If you have a distribution of initial conditions, that doesn't change the late time physics. So I'm going to make this approximation just for simplicity, but this is what you get: minus bi tau divided by sum over j, e minus ej tau, where bj is minus 0 to tau d to prime cj to prime, and that's assuming, as I said, mu I 0 is equal to 1 for all I. And that means that, bj is a Gaussian variable, and bj tau bj to prime is equal to bi delta ij. So this formula shows that the statistics at finite time of the news, it's actually, up to this proportionality constant, it's exactly the probability weights in the random energy model. So the statistics of mu I is that of the weights in the random energy model. So let me recall the usual formulation of the REM. In its usual formulation, you have 2 to the n degrees of freedom. Or configurations, not degrees of freedom, 2 to the n configurations. With independent Gaussian energies, calling them epsilon I, with epsilon I square, the variance is of order n. And at finite inverse temperature, beta, the probability of state I is Pi is equal to E minus beta epsilon I divided by the sum over j, E minus beta epsilon j. So it takes exactly the same form as the solution for the relative abundances nu I. And what happens in the REM is that as n goes to infinity, for beta small temperature, small temperature, sorry, beta T, which is square root 2 log 2, there is a condensation transition, and the thermodynamics is dominated by Q deepest energy state. Now, if you see that here you don't have 2 to the n, but s configurations, and that the amplitude of the noise is not n, but is tau, that corresponds in the larger regime this corresponds
S is 2 to the n, exact. S is 2 to the n.
so yeah, the mapping is s goes to 2 to the n.
Beta is
So you have beta n, which is equal to tau. So this corresponds to a condensation on a few degrees of freedom in times tau that scales as log n. So very rapidly, you just condensate on a few degrees of freedom. The others are exponentially small, and so if you once more, if you put any mechanism that would allow for extinction, you're just going to end up with a finite number of species very rapidly.
What is the difference between this model and the one of the web condensation of Pirey? Remember? They have a similar model.
Yeah. So okay, so you're right. It's also in there. The paper, the more recent paper that I wrote with Jean-Philippe, but it's true that Mark is not in this one, also takes the same idea and extends upon them.
But what is the new ingredient of the original model? I don't remember. Because I don't remember the original model.
So I think up to this point, for the epsilon equals 0 case, it's pretty much like the original model.
And for instance, when one thing also your precise dynamics, some suggestion for the dynamics of array around the manager model. Because I'm sure around the manager model, people studied also some dynamics. Are they similar?
I don't think so, because I think mostly what they do is activated dynamics.
This is the dynamics, basically, not the dynamics of
Yeah.
the configuration.
Yeah,
space,
exactly.
it's different.
It's the dynamics on the probability, I mean, on the state of probabilities. So, yeah.
Yeah, different, but okay, I don't know the field, but I asked someone, he's a motor shop, who is in the random manager model, and so he said, oh, it's not like in ferromagnet classical, whichever we have somehow good dynamics, like louder dynamic properties, whichever. Over there, I guess it's no less, no, less different.
No, you
Be
can do
different. You can do, but different. People suggested different things.
Yeah, you can do.
So that one can also think.
Just once more, I agree with what Francesco said. This would not correspond to dynamics of the states described by random landscape. Okay, so this is what happens. So this is a bit the equivalent, in a way, where the noise is external and does not obey the self-consistency condition. It's a bit the equivalent of the aging regime that happens when you have disordered interactions. You're still very much attracted to these absorbing boundary conditions at small population size, and eventually the fluctuations are, I mean, the diversity drops down to just a very small number of species. And this is what happens without space. And what I just want to introduce now.
Sorry, Thibaut.
Yes.
What do you mean by what do
Yeah,
you
next
mean
week.
by few?
Finite numbers. So I mean, the thing is, the more you run, eventually you have only one. In time, log s, it's a finite number, and then over time, that scale at log s, that's where this finite number would eventually go down to one.
And that means one species. Well, one energy state corresponds to
Yes, exactly.
few species.
Okay, so I'll just introduce the model and leave it. But first, I wanted to comment a bit on this notion of space. So, a non-well mixed model the crucial ingredient is that, as far as these kind of population dynamics models are concerned, is that deleterious fluctuations at one place can be compensated in principle, by beneficial fluctuations in neighboring locations. And so at the single population level, so just assuming you have one population, not a many populations as we've done so far. The paradigmatic example is the directed percolation universality class. So the concept of directed percolation was not introduced for population dynamics, but it comes from this work in 57, and that was to introduce an anisotropic generalization of the percolation problem. So it's a geometric interpretation of the directed percolation. And so, and the corresponding field theory, which will make the connection to population dynamics transparent. And that field theory is known as Reagan field theory. And that's a name from high energy physics, because similar thing appeared in high energy physics. And so it's the stochastic logistic growth equation with a diffusive term. And this is a space-time Gaussian white noise. So eta xt, eta x prime t prime is equal to delta x minus x prime, delta t minus t prime. And that's E2. Or it's bigger, it's very small. So it's stochastic logistic growth with diffusion. And the phenomenology is that there exists a critical growth rate RC such that, and that's an absorbing phase transition, for R less than RC, the average of n goes to 0 as time goes to infinity, so the population goes extinct, and R larger than RC, the average of n in the in the limit of infinite size goes to n bar, which is strictly positive as t goes to infinity. So so that's transition from passive to active or absorbing phase transition. There is different names. And so that's the most paradigmatic example. That's why I introduce it. I'll come back to GP more precisely next week. The second part of next week's lecture. For this chapter, I want to look at something a bit different. And we will disregard the demographic noise. And focus on the spatially extended version of the previous model. So what I want to look at is this, dt ni xt is equal to ni r plus sigma psi xt minus epsilon ni minus mu sum over j and j plus d Laplacian ni, where these now are space-time motion white noise and correlated across species. And I'll be even more restricted than that, because I will look at the mean field version of that on the fully connected lattice, spatial lattice. So we will restrict to the fully connected lattice. So what I'll be really looking at is this. So Q sites. So dni alpha dt is equal to ni alpha times r plus sigma psi I alpha t minus epsilon ni alpha minus mu sum over j and j alpha plus d divided by q sum for beta equal 1 to q ni beta minus ni alpha. And here alpha is the site label. So alpha beta are site labels. And with the same condition, psi alpha t psi j beta t prime is equal to delta ij delta alpha beta delta t minus t prime. And I'll just conclude by giving the relevant reference for the discussion that will follow. And the discussion that will follow will be actually some kind of pedagogical, digression around the paper that follows, mostly. So it's Al Iasat, Swartz, Gore, and Kardar. And it's archive 2602. And so I will stop here for today. Any questions?
So this is very interesting. First, you study one species that depends on space, and then you introduce many species. I mean, the model seems to be very different. I see the connection.
So you mean with the directed calculation?
Yes.
Okay. So this idea that, I mean, when you think about space, the main idea is that if things go bad somewhere, things can hopefully go good somewhere nearby. And then because you're connected, you can compensate deleterious fluctuations due to that. And the simplest setting in which you have this mechanism is really directed percolation. It's a single population. Well mixed, it would go extinct in finite time, that we know. I mean, that's what we did. Maybe the time would be exponentially large if the noise is small, but it would go extinct. Now, if you start having space, then it might go extinct locally, but global extinction is prevented because you have migration from nearby places. So that's the simplest setting in which this exists, and it's the most well-known, most studied setting. But now, what I'm interested in is really like coexistence of many species or interactions with many species. So this is the model that I'm going to study. And then I want to see how and if the mechanisms that I was describing, which is not tied to a specific model, works out in this case and allows the survival of a large number of species, unlike the well-mixed case where what we see there is condensation on a finite number of species.
But for instance, in your first example, you have some noise like this psi, but in that the calculation, noise was proportional to
square root.
noise.
Yeah.
This arena proportional.
Yes, you're completely right. So it's relevant so indeed, if you take a single species model with demographic noise and with environmental noise, as long as this one is short range, then the universality class is directed percolation because square root of n wins over n when n is small. Basically, I mean that's the most relevant operator. Here I'm somehow neglecting it. It turns out that for what I want to discuss, it works out provided that the amplitude of the demographic noise is small enough compared to something that we'll find next time. So I'm not going to span the entire phase diagram and approach arbitrarily close to the critical points. Not what I'm going to do here. So assuming that the noise is small, demographic noise is small, I'll be in a regime where.
So when you introduce space, it seems that one can think about noise, which is, just this space is good, like plants, plants grow well, and Sahara is not so good. And so it depends only on X and not on time.
Okay, so that's not what I'm describing here.
That's not what you described.
Yeah.
But for instance, you want to take Venus, we have one paper, we call it as a joke ecology paper, but over there it was noise like that, Noise was, just
Frozen.
Quenched.
Yeah, quenched.
dependent only on space. And it was also amplitude was not root of n, but exactly n.
Yeah.
And it was just some, without minus n squared term, it was just unbelievable. It was, for instance, immediately blow up at time t equal plus 0 in 3 dimensions. In the finite can blow up in 2 dimensions, but in 1 dimension it was extremely fast growth, but blow up. So really spatial dimensions play a great role, and definitely it's very important noise being in a place.
I completely agree with you. So the one thing I can say is that those are all great questions. That in this, in the framework of directed percolation, we sort of know what happens when you add a quenched environmental noise. When the directed percolation transition is destroyed, it's not DP anymore. So that we have kind of understanding. What happens for models of many species coexistence with quenched environmental noise? Not here. What happens for this model in finite dimension? Not clear. So there are many gaps here. And so I don't have much better to tell you than this is where we are at the moment, and I'll present you that, and that pinpoints to ways about how to study the finite dimensional case, but the analysis has not been done. And if time permits, at the end of next time, I'll go back to finite dimension in a slightly different setting, a bit closer to directed percolation, but if time permits.